you were younger, you didn't realize all of the science involved in swinging. And little did you know that physics is all around you. And today we're going to discuss simple harmonic motion. Simple harmonic motion is just a back and forth movement, also called oscillation. And we're going to get an example of that right now. So this swing is an example of simple harmonic motion. And we're going to get some help from my good friend Raji. Hey Raji, nice to meet you. Hi, thanks. Okay, so when Raji's swing is at the middle, right there, that's the equilibrium point. And the swing reaches the equilibrium point from the restoring force, which is the force of gravity pulling the swing to equilibrium. When the swing reaches the high point, the velocity or speed is 0 because it stops just for a really short second to be able to swing back the other direction. And the restoring force is maximum because the gravity is trying to pull the swing back towards the middle. Public service announcement: swings aren't the only thing that can be examples of simple harmonic motion. Another example would be grandfather clocks like this. How fun is that? Because physics is life. Okay, so before we get into the mathematics of the spring, I'm just going to explain the basics. So, the motion of the spring is oscillation as well, and it's just like the swing, except that it goes up and down instead of back and forth. So, equilibrium would be right when it's in the middle of its period, yes. So when it's at equilibrium, again, the velocity is maximum and the restoring force is 0. And then when it's at its height, or the longest crest, it would be at its maximum restoring force and 0 velocity, which is similar to the swing, just that it's different motion. Okay, so to further explain simple harmonic motion, I have my good colleague Dr. Hook here, who has a very special equation for us. Let's give it up for Dr. Hook.
Hello, I'm Dr. Hook.
Can I have your autograph?
No, get away. I am the creator of Hooke's Law, and what my law claims is that the extension of the spring is directly proportional to the mass added onto it. Let's see this in my example. So this spring has 2 keys and this one has 1. And when I drop it, you can see that the one with 2 keys goes lower because the mass on it is heavier, therefore pulling it down more. We also have an equation to represent that. It goes like this. F equals negative kx. F is a force, k is the spring constant, x is the displacement.
Okay. Now I want you to meet my favorite teacher, Miss Galeritis, and she's going to talk to us about our last segment, period and frequency.
Hey kids, although swings and springs don't seem all that similar, they both can be measured with something called period and frequency. A period is the time it takes to complete one cycle. In other words, how long it takes to go from a starting point and back.
If you want to know the math side of things, we can go through these 2 equations. The first one is the period for a pendulum, which goes T equals 2 pi square root of length over G. Here the T is the period, L is the length, and G is the gravity. The one for a spring goes T equals 2 pi square root M over K. Here's the same thing with the T is the period, M is the mass, and K is the spring constant. Let's go through some sample problems now.
Whoa. Okay. I think you need to just calm down a little. We got the equations. We don't want to bore the kids. But thank you so much anyways.
Frequency is how many cycles are completed in 1 second. For our real world example, we will time how many times Bridget can swing back and forth on on a swing in 10 seconds, and then divide that by 10. Are you ready? 1, 2, 3. Stop.
Okay, we already talked about the period and frequency of a pendulum or a swing, but now we can see how it looks on a spring. Okay, so here, so we have the different parts of a spring, and a period is when it starts here, and when it gets back down. So it'd be 1, that'd be 1 period. And then frequency is the same, so how many times it comes back down in 1 second. Okay.
It's important to know that the only thing that affects the period of a pendulum, or in this case a swing, is the length. A shorter swing will have a shorter period, while the longer one has to go farther to get back.
It isn't affected by the mass on the end of the pendulum, so it doesn't matter if I'm on the swing, or my dog, or my dad.
What doesn't affect the period is the height. Even though a person is holding her swing farther back than me, the period still can be the same.
Well, I hope you enjoyed our show today. So remember, next time you're on a swing, just remember everything you learned about simple harmonic motion. Because remember, physics is all around you, and physics is life. So thank you for watching, and have a forceful day.
I fell down, down, down into this dark and lonely hole.